Hello everyone, welcome to PhysicsMage. Dear students, today we'll have an interesting problem which involves the ideas of fluid statics as well as a little bit of mechanics. So let's try and solve this problem. An open cubical container of side H is filled with a liquid up to a height h by 4. Mass of the liquid inside container is m. Neglect atmospheric pressure. When container is moved with maximum possible acceleration, what will be the value of force applied by liquid on front wall parallel to the plane of the paper? That is our question. So dear students, here we have some liquid here. Okay, this liquid is present in a cubical container, and this cubical container is getting accelerated, not just some acceleration. We need to consider maximum acceleration such that the liquid won't come out of the container. Okay, so we need to find out what will be the force offered by the liquid in such a condition onto this front surface of the container. Okay, so dear students, a quick recap of what you should know. Suppose if you take this as a container containing liquid, okay, so you should know a little bit of ideas like if atmospheric pressure is P naught and if the liquid has density rho and acceleration due to gravity in this space is g, then when you go deeper into the liquid to a distance y, at that point, let me name that point as some s, that point s will have the pressure being equal to p naught plus rho g y. This is something you should know. Okay, and also you should know, like, suppose if you take this elemental mass, meaning if you take a small portion of mass here, I'll be selecting a small portion of mass which I name it as dm. So whenever we think of it is in equilibrium, what is the meaning of it? See, fluid statics meaning the liquid should be at rest with respect to the container. So meaning this dm elemental mass we are taking, right, that is experiencing acceleration due to gravity, right? So as a consequence, it will have its weight acting downwards. But because of the liquid arrangement around this dm, it will experience force upwards, and this upward force should be cancelling the weight so that it is not moving, it will be at rest. Whenever you say fluid statics, this gravitational force, right, weight, that is balanced by the force, and this force comes due to the pressure difference. Because of pressure difference, this force will come up, and this pressure difference will ensure to balance this dm. So dear students, probably you know this, because of this pressure difference itself we'll have buoyant force and all if some other body we immerse here and all. So probably you know all those things. So we derive the idea of rho gy from this balancing condition. Okay, so you must know this. Once you recognize this force, right, pressure difference force, in if you consider imaginary lines which are perpendicular, imaginary lines, let me choose like this, these imaginary lines which are perpendicular to this force, those are considered as equipressure lines. So as we go deeper and deeper into the liquid, we have higher and higher pressures, but at the same level, when you say the level, in this level pressure remains same. Got it? So I think you are all aware of this. Just a recap here for those who have a little bit of problem in that. Now, once you recognize this, what next? Now let's take the container which has some acceleration now. If this container is subjected to acceleration, let's say, then definitely liquid won't be like this where the surface is horizontal. We know that the surface will turn out to be a tilted one like this. Okay, so why it is tilted, that is a different story. We'll have a quick observation of why it should be tilted now. Okay, Sir, will it be tilted if it is moving with constant velocity? No. If it is moving with constant velocity, no. But if it is moving with acceleration, it gets tilted. Okay. So here we know that it is accelerating, right? So for simplicity, let me take here some elemental mass. Okay, dm, elemental mass. This dm fellow, I'm just looking at FBD of dm fellow. Okay. So dm fellow will experience acceleration due to gravity, right? So meaning it will have its weight acting downwards like this. And since now we are dealing with fluid statics, when we say fluid statics, it means that fluid should be at rest with respect to the container. So with respect to the container, meaning it is container's frame. In container's frame, we have here this pseudo force will be acting in the opposite direction. So why should we have this? Because there is non-inertial frame. So as a consequence, we need to take acceleration in the opposite direction. Correct? No. So these are the two forces here. Now these two forces should ensure that dm should move in this way with the net force experiencing on it as root of a squared plus g squared times of dm. That's the net force. That's a force it should be experiencing because of these two fellows. But since it is fluid statics, so we know that there will be a countering force which will be acting exactly in the opposite direction like this. This force is due to the pressure difference. This is because of pressure difference. Okay. Yeah. Now, once you recognize this, you can easily observe why we have that tilted water surface. Okay. This is a tilted water surface here. Now, if you name this angle as theta, meaning this angle is theta. Now you can extend this line and call this angle turns out to be theta, angle between the lines, angle between their perpendiculars. Okay, so this is theta. So from this diagram, you can easily recognize that tan theta is going to be dm times a by dm times of g. Correct? So tan theta is a by g. This is something which we can analyze. And also, I want you to recognize the equipressure lines here. See, this is a top surface, right? This is a free surface. So all these equipressure lines will be parallel to this surface and it will be shown like this. So meaning, suppose if you observe the point here, these bottommost points, right? See, all these yellow color dots, they all will be at same pressure. They all will be at same pressure. But here, now this is at higher pressure when compared to other points. Suppose if you consider this red color dot and yellow color dot. So yellow will be at higher pressure when compared to red because it is at much deeper level. Let me highlight that. See, from here it is at much deeper level when compared to this one, red color dot. So the yellow color dot will be at higher pressure. So pressure here is high. Okay. So that is something which you have to recognize. So once you recognize this at certain depth, let's say if you will go to the next slide and we'll see that. Suppose if you consider there is a container like this and liquid in it is in this way. Okay. Liquid here is in this way. Now, since we can easily recognize equipressure lines, right? These are equipressure lines parallel to the surface, equipressure lines parallel to it. At any given depth, suppose if you choose one point and if you say that from the surface you drop one perpendicular, this is perpendicular. If this is at a depth, then if you consider atmospheric pressure P naught, we have P naught. Then at that point, if you name that one as point A, let's say, pressure at the point A would be P naught plus rho G effective times of Y. So difference between this one and the previous one is, the previous case, we have equipressure lines which will be horizontal. Now equipressure lines are tilted and we need to take G effective rather than just G. So what is this G effective? G effective is the force due to pressure difference divided by the dm fellow. Okay, so you have here force due to pressure difference, that is dm root of a squared plus g squared, right? So we can easily recognize this is root of a squared plus g squared. This is what we have here. Okay, now these are the basics one should know before we try and solve this problem. Okay, suppose if you know already all these things, then we can directly solve this problem. Let's go ahead with this problem. So given problem has a cubical container. Say this is h, it seems. This is also h dimension, and into the screen also h dimension. I'm not showing it for convenience. Let me show like this. This is also h dimension. Okay, then we do have liquid filled all the way up to h by 4 amount of height. This is a liquid filled, correct? So to a height of h by 4, correct? So initial volume is going to be h squared times of h by 4. So it becomes h cubed by 4. But dear students, once this container starts accelerating, this liquid will not be like this. It will be tilted like this, correct? So it will get tilted like this, okay? Meaning even more deeper like this, gets tilted, and it may look like this, okay? So we know it will get accelerated this way. Yeah, so I'll be rewriting this diagram only in 2D way, so it becomes easy for us to visualize. Okay, let's say this is under maximum acceleration here. When we say it is maximum acceleration, when liquid reaches all the way up to the height h, okay, that is the maximum. Okay, so liquid is all the way up to this one, and here we don't know whether uh, like what is the length this side, that and all we don't know. Let me name this is some s distance. Okay, now if this is s distance, then we have the volume now as half into base into height times the other dimension into the screen is also h, right? So it is h squared s by 2. So using this we can find out s. So comparison here, so s is going to be h by 2, just equating volumes equating volume, you will get s is equal to h by 2. Okay, so once you get s is equal to h by 2, then we can predict this angle theta. So tan theta is going to be h by h by 2, right? So which is nothing but 2, and we also recognize this tan theta is a by g. So indirectly we got this information that acceleration, if it is 2g, this is the maximum acceleration possible. If you go slightly above this acceleration, then water will come out of the container for the given story. Okay, so this is our initial observation. Okay, now what next? Now I will take it to the next slide and show you like how to compute the force. Suppose if you take this as our container and liquid present here, say from here all the way to the half, right? I'm just roughly writing. Okay, so let me name this is A B line. Okay, and this point let me write as O, and I'll be dropping one perpendicular like this. This is a perpendicular, consider. Okay, and suppose if I want pressure at a point P, let me say this is a point P. At that point P, I need pressure. Okay, so atmospheric pressure, they are saying that to ignore. So if you ignore the atmospheric pressure, all we need is the depth. Okay, suppose if I say this is y amount of depth, if you want we can take this as y, or let us keep it as variables as of now and name it as let me say this point is c. So pc is the depth. Okay, p to c is the depth. P to c is the depth from what? Liquid surface. Liquid surface. Okay, now going further, just to think of equipressure lines, we know that equipressure lines will be parallel to the free surface or water liquid surface. So can we consider the line which has same pressure as the point P will be this line, correct? See here, this point P will have some pressure, right? So every single point on this purple color line, right? Every single point on this line will have the same pressure. If it has the same pressure, then we can find out the force exerted on this elemental area. See, for this, we are going to consider that this one has a thickness dx, let's say. And from here, from O to P, that distance is x. So O to P, that distance is x. Then what about P to C then? P to C is going to be, if this is theta, then we just found this distance as h by 2, right? And this is h amount of height from A to O. So we can write now O to C, O to C minus O to P, that is PC, correct? So O to C is h by 2 sine theta and O to P is x. So we have PC value as this. Yes, students, here just now in the last slide we got tan theta as 2, right? If tan theta is 2, then we can comment on sine theta. So sine theta is going to be 2 by root 5, no? So we can write h by uh, root 5 here minus of x. That is PC value, PC. Okay. Then going further, what will be the pressure at that point P? The pressure at the point P is going to be density of the liquid G effective times P to C. Correct? No. So P to C, we need that. So P to C we already have here. We'll substitute that. And G effective also we have. So let me substitute all these values. This is going to be root of A squared plus G squared. And P to C is H by root 5 minus of X. Okay. So I'll be writing density as it is. See, acceleration, because acceleration is 2g, no? So we can write this one as g times of root 5 here and h by root 5 minus x. That's what we have here. Okay, root 5 minus x. Okay, now what is the small force acting on this portion? Let me consider this purple color shaded portion. This is an elemental area. So let me say C, not C. Okay, E to F, let's say E to F. So E to F, right? That length, let me name that E to F length. E to F length as Y, okay? E to F length is Y. If that is the case, then small force exerted on that patch of area is going to be pressure multiplied with the small area. Pressure into area gives me the force, correct? So this pressure we already have here, that we can write here some from using equation 1, let's say. From using 1 we can write here, and dA value, dA is how much here? So E to F is the length and the thickness we can name it as dx. Dx is the thickness, that is the small force. Now we need E to F value. E to F is y times of dx, right? Now how do we compute this? We need to depend on calculus approach. So first let me write all these things and see how many variables are involved. We'll try to convert everything to one variable. Okay, so rho g root 5 and h by root 5 minus of x into y times of dx. Yes, students, here if I change this y in terms of x, then everything will be in terms of x. Then we can integrate from like O to C so that we can compute the entire force exerted by this liquid onto the front surface. Okay, that's a plan. Now to get the value of this y in terms of x, I'll be just highlighting this here once here. See, from E to this F, right? This entire length is y. That is y. Okay. Then what next? You should also recognize that A to B, A to B, this entire length, A to B, this entire length, if this is h and if this is theta, A to B, right? That is h by sine theta. H by sine theta is the length from A to B, right? So I'll be writing that here just for identification. So A to B is going to be h by sine theta. Okay. Now, since we already know that sine theta is 2 by root 5, let me write 2 by root 5 here. So h root 5 by 2 is AB length. So using similarity of triangles, we can say from triangle OEF and triangle OAB, we can say that triangles are similar, so their sides are proportional. So x by y is equal to, we have OC length as h by 2 sine theta, h by 2 sine theta divided by the AB distance. AB distance is h by sine theta, right? H by sine theta. So it turns out to be, it is sine squared theta by 2. That's what we have here. So using our logic of sine theta as 2 by root 5, if you use 2 by root 5, it becomes how much here? Let me write here itself and complete this. X by y is equal to, see, sine theta, no, it is 2 by root 5 squared, so it is 4 by 5, and there is 2 in the denominator, it gets cancelled out, so I can write directly this is 2 by 5. So I can write y is equal to 5 by 2 times of x, correct? So y here is going to be 5 by 2 times of x, that is our y, and dx here, that is equal to rho g times of root 5 and h by root 5 minus x. That is our small elemental force. Dear students, we have written everything in terms of x. Now we have to just integrate from O to C, correct? So let's do it and get that integration. I will take it to the next slide. So the small force, when you integrate, it becomes total force. And that turns out to be how much here? See here, rho g root 5 is constants, and 5 by 2 is also constant. So I'll be writing 5 by 2 constant outside the integration. And we have h x by root 5 minus x squared by 2, right? Minus x squared, 5 by 2 I have taken, x squared, this into dx, that I have to integrate. Okay, so I'm just verifying h by root 5 x minus x squared. Everything else I have taken outside the integration. Now here, as we move from O to C, we know that x varies from 0 all the way to h by 2 sine theta, right? So 0 to h by 2 sine theta. So what will be the force? We'll check. So we have rho g 5 root 5 by 2, and this one, as we integrate, this is h x squared by 2, x squared by 2 root 5 minus x cubed by 3. We have h by 2 sine theta and 0. As we complete this integration, we have 5 by 2 here. As we substitute this limits here, yes students, we know that h by 2 sine theta, no, sine theta is 2 by root 5, we already know that. So we can directly write this h by 2 sine theta as h by root 5, h by root 5, because sine theta is 2 by root 5. Okay, so let me substitute the upper limit. It turns out to be h by 2 root 5, we have this h squared by 5 we'll have here, minus this is going to be h cube by 3 5 root 5. See, we have 5 root 5 whole cube, right? So 5 root 5 I'm writing. I think that's fine with the computation. Like say root 5 whole cube is 5 power 3 by 2. It is 5 root 5. Okay. Now using this, let me take a few things common. So dear students, lower limit, even if you substitute, it doesn't matter, no? So I'm not writing it separately. So I'll be taking 5 root 5 from the denominator common and h cube from the numerator. So if I do that, we'll have 1 by 2 here minus 1 by 3. Okay. So 5 root 5 getting cancelled out. We have rho g h cube by 2, and this turns out to be 1 by 6, correct? So using that, rho g h cube by, this is going to be like 4 times of 3. We can write like this. Okay. So this is a force acting on it. Dear students, initially the story goes like this, right? So initially m amount of mass of liquid is present in the system. So m amount of mass was present, like density of the liquid into the volume. Volume was initial volume here. That is h cube by 4. This was the mass, right? So using that logic, rho h cube by 4 is mass. So mg by 3. So the force exerted by the liquid on the front surface of the container is found to be mg by 3. So dear students, I hope you understood this problem. And if you have any doubts or queries with respect to it, please post that in the comment section. Thank you.